Hello from Dendrite Digital in Anaheim, makers of the Virtue Data Processor. So on the left side of the graph here we have the initialization of a rather large dual port block RAM. It's not large by computer standards, but it's large in terms of the space on the Arctic 7 200T. So it's 64 bits by 128K. So that's a good sizable chunk of the RAM. It's actually it's like 70%. So 70% of the block RAM. I couldn't go up another bit of space in addressing. It's only 17 bits, 128K by 64 bits. And you can see over here on the left that it's not initialized. And you can see both addresses counting up, making sure that all of the RAM is zeroed. So let's back up a bit. You can see that it's not initialized here, but once we get to this point, from then on, it's all green. So we're sure to get some interesting results. You can see the randomized address is toggling before you can see that it's waiting a clock cycle before making the data available. And so how does this work, huh? You're asking. I want to make a dual port RAM on my FPGA. Well, I'm going to show you. And we're just going to take this out. Actually, why don't we look at the code here? It's probably a lot easier. So, actually, yeah, here it is. This is the good stuff here. If we go down to the bottom, here's the this is just 1 byte. You can see both the data out and the data RAM. The data in the RAM are both 8 bits, but we fixed that later. So I'm doing it 8 bits wide, so it's byte convention. And you can individually select the write byte. You got 8 bytes wide, 64 bits, and you can individually write 1 byte or any combination of bytes to the output. And so that's kind of a neat way to do it. And then here we're initializing our 2 output ports from the RAM. And here we have our 2 ports, a CPU port and a GPU port. And they can both write to the RAM and read from the RAM. And here we have our ports. So I'm using the same clock. I tried to get it to work with 2 clocks. It didn't seem to like it. But I'll try that sometime later. to do 2 independent clocks. I'm told by a reputable source that you can have different clocks for the 2 ports. And then here's the magic. Here we're taking 8 bits at a time, and we're stitching them all together into 8 individual RAM chips. These are the module we just looked at, the RAM 17 right here. So we have a clock, and notice we have 8 lines of write select, and then we have the CPU address, and then we have the CPU out. This is going inside into the RAM from a CPU that's 64 bits wide. And then here we have the CPU RAM, which is the data coming out of the RAM into the CPU. And then we have the same for the second port, all running on the same clock. It was just easier that way. And then here's our ports. Looks real similar to the RAM 17, except that now we have 64-bit ports instead of 8. And then up here we have our simulated CPU, and here it's randomizing. Here it's randomizing the data, and here it's initializing the data. Remember, both of these were initializing the RAM simultaneously. Yeah. See, they're probably same address all the way through. Just making sure it's all zeroed. You can see that they're both following each other, simultaneously checking, and it takes the 0 from the CPU out and puts it into the RAM at this address, and they're both doing it just to make sure. And then so you're asking, what's the top level look like? What's the top level look like? So that's your CPU, similar thing with the GPU. And then here's our LFSR that I'm using to test it. And here, let's look at this from the top. So this is the simulation code for initializing the. This is the outputs that I don't need in the finished design, and this is just a port to randomly select one of the memory addresses. I'm using the CPU port, and I'm just right here selecting one of the CPU ports, 8 bits at a time, and that way I'm sure, and the GPU address and write ports. Actually, I don't have the right port for that, but anyway, so here we're instantiating the entire RAM, dual port 64-bit by 128K. 128K works out to exactly 131,072. And then here, and I'm using much larger addresses in the event that I'm able to get a bigger FPGA and make the RAM bigger. That's not going to be for a while. My finances aren't what they need to be. So here we're just selecting a random bit of data coming in through the RAM byte. And here's the RAM byte. And we're just randomly selecting one of these bytes from the inputs or the outputs from the data coming from the CPU, the RAM, and the GPU. And so you're going to want to see this compile all the way into a full-fledged module on an FPGA. I don't know. That's going to come later. I want to do some interesting things with this, and have a GPU and a CPU accessing this dual port RAM in my VRGC Virtue Realizer game console, and again, I'm the inventor of the Virtue Data Processor. I'm still working on it. It's getting close. So here we are in Vivado. Here's our dual port RAM project, and this is implemented design, and it's showing some good numbers for the timing. Methodology still has a few complaints, but you know, what can I say? Sometimes it just doesn't work the way you want it to, but everything's looking pretty good. Here's the power consumption. Here's the methodology. Again, it's got a critical warning about timing, but over here we're still getting good numbers, and it's not complaining up here about the failing timing. So I think it's a good deal. And if we look at the log, so we'll go all the way at the top. This is implemented. Here's implemented. Let's watch it from the beginning here. So lots of infos. I got a lot of modules. (64-bit) memory, 24-bit address, 12 bits for write bits, which byte to write to. I don't know if there's a need for 12 or just 8. I like 9 because it's divisible by 3, 6, and 9. 9 bytes divisible by 3, 6, and 9. And then here's our 8 bytes of RAM that are 128K by 8 bits. Yep, here they are. And more of the same. And then this mess. It just goes on forever. Da-da-da. And it even gives up. It says, appear 100 times and further instances of this message will be disabled. Further messages will be disabled. Length. Width. So that's synthesis. And here's implementation. Got 16 here, but nothing preventing optimization. So, and that's it. And then if we look at the code one more time from a little bit different perspective, so here's a little line that I turn off so I can do the simulation and get all my outputs. And then here they are again, but this time with N in the if not defined debug. Then I still want those ports to be spelled out to the right size. And we have a little randomization here for the RAM byte. Here's 16 different RAM bytes coming out of the unit. That's so it won't optimize anything out of the design. You got to use LFSR or it's not going to work. It's just going to stub them all out and optimize it out to nothing. If you just initialize it all to 0, it won't work. Or any other number. It'll just optimize it all. And then here's the LFSR, 24-bit and 64-bit. Here's the GPU. It's real simple. It just initializes and then randomizes. The GPU goes sequentially here on the address, and the CPU randomizes the address and works on the write bits as well. So and then of course this is our 64 bits. We're doing 8 bits at a time. If you try to put it all in one RAM, you might have some problems with unmanageable width, and the Vivado won't know how to synthesize it right. So you break it down into 8-bit bytes and multiplex them all together. Just give it a different 8 bits to work with. and line it up on the GPU and the CPU, each with their own write bit, and that way you can individually select just one byte out of the 8. And then here's our module for doing the dual port RAM. So here's the RAM, 8 bits wide by 128K. Be sure to do a -1 here, or it's gonna figure that there's something wrong and optimize it out later. If you go too low, it'll still synthesize, but it'll be weird. It'll be 127K instead of 128. Something weird will happen. And then here's the guts of it. Here's the RAM. So here we're writing the byte, and here we're reading the byte. And you always want to read, but you don't always want to write. Got to check the write bit. Here I have it active high instead of active low. You do it either way. I just don't like to add the _n on the names. I like these six letter names. They make it so much easier to edit. And here we have the CPU, and here we have the GPU. Both independent addresses. CPU, GPU, independent addresses. And independent output ports. Independent input ports. So you can read and write and however you want to do it. And I think it will take precedence on the GPU if the same address is here in the CPU. So, I don't know. Maybe I should reverse this. I don't know. Thank you.